Hello, everyone. I'm Jackson Perkins, and this is Team 15 here to talk to you guys about flows in porous media. And so first, what is porous media? So any solid material that contains an internal pore structure, either empty or filled with fluid, is considered porous media. And so flows through porous media are more complicated than just typical internal flows. And so we're going to walk through some terms and equations here today to better describe flows through porous media that can be calculated in real world. And so a few real world applications before we begin is crude oil movement through rocks during underground extraction. If we're trying to pull oil from underground, a lot of times it has to flow through other sediment and rocks. This is a great example of flows in porous media, as well as biological tissues, where blood vessels act as pores and interstitial space and cells act as solids. As seen in this diagram here, this is a great example of flows through porous media. And so the first thing we're going to talk about is a few terms, a few values used to describe flows in porous media. The first is specific surface, which has the units 1/meters. And the formula is the total interface area divided by the total volume. We also have the porosity here, which is the void volume over the total volume. And these can seem a little abstract, but this example should help make it clear. And so here we have a rectangular prism with a cylindrical pore running the length of it. The prism has length L and the pore has diameter D. And so here we can see the square cross-sectional area is A. The total interface area would be the contact between the pore and the surrounding solid. So the surface area of the cylinder basically without the end, since it is not contacting any solid. So it would be pi D times L. And the total volume of porous medium would be the total volume of the prism. So the area of the face times the length, AL. And then the void volume in orange is the volume of the cylinder, which is D squared over 4 pi L. And so from that, we can calculate the specific surface and the porosity. As seen here, the specific surface is the total interface area, so pi dl over the total volume, AL, which simplifies to pi d over A. And the porosity here is the void volume, which is D squared over 4 times pi L over the total volume, which is AL, which simplifies to pi D squared over 4A. And so we have an example here. It says determine the specific surface and the porosity of a porous medium with uniformly distributed cylindrical pores. Assume the pores are parallel to each other. The diameter of the pores is D, L is the length of the pores, and the number of cylinders per unit cross-sectional area is NA. N is the total number of cylinders in the material and is equal to the product of the cross-sectional area A and NA. So basically we have like our last example, except we have more than one pore. And so I'm going to throw up a few values here, a few calculations. And so first we have N, which is the number of cylinders, is equal to the number of cylinders per cross-sectional area times the cross-sectional area. We have the total interface area, which again is the contact between the pores and the solid. So pi dl times N, since there's N number of cylinders. We have the total void volume, which is the volume of one void times all the voids. So pi d squared times the number of voids. So D squared over 4 times pi L times N, the number of voids. And the total volume is just the volume of the rectangular prism. So A times L. And I want to throw up the specific surface and porosity values or formulas here. And let's see if we can calculate them from what we have so far. And so the specific surface is the total interface area, N pi dl over AL, the total volume. Which simplifies to N pi D over A. And we can simplify N over A using this equation at the top. N over A simplifies to NA, which leaves us with pi D NA. We can do the same thing for the porosity here. We have the void volume, which is D squared over 4 times pi LN over the total volume AL, which simplifies to D squared times pi N over 4A. And again, N over A simplifies to NA, as seen here. Next, porosity doesn't really describe the type of pore or the flow through it for different kinds of pores. And so we can see here that we can divide pores into a few categories to better describe them. First, we have penetrable pores, which include passing and non-passing pores. We also have isolated pores. As seen here, a passing pore goes entirely through the medium. A non-passing pore is still penetrable to the outside, but not all the way through. And an isolated pore is not exposed outside of the medium at all. And so porosity can be described as the sum of penetrable and isolated pores, as seen with this formula here. And the void volume only includes the volume of penetrable pores. So when calculating the void volume, do not include isolated pores since there's no flow through them. Now we have another term. So path length through porous medium can also be used to further describe the transport of the porous media. And so here are a few terms that we can define, which is L, which is the shortest distance between 2 points. We also have L min, which is the actual minimum distance traveled by the fluid. Now, tortuosity is defined in order to relate these two length values. And so it's defined here, where tortuosity T is L min over L squared. And by definition, this has to be greater than or equal to 1. So if we look over here, we have an example. And so we have a porous media here, and we're going from point A to point B through this solid. And so L, the blue path, is the shortest path from A to B, which using these values provided is square root of 2 meters. And L min, which is the orange path, is the path that the fluid has to take through the media, and that just happens to be 2.5 meters. And so from that, we can calculate the tortuosity, which is 2.5 divided by the square root of 2 squared, which equals 3.125. And the tortuosity is a dimensionless value.
Introducing the available volume fraction. So to start, not all pores are able to be accessed by certain solutes. An example of a case where this might happen would be that the size of the solute, actual molecule, is larger than the size of the pore. Available volume is the section of a pore that is able to be occupied. And the available volume fraction is the ratio of the available volume of a pore to the total volume of the pore, and it's denoted by KAV. And the available volume fraction is always smaller than the porosity and always molecule dependent. So there are 3 cases where this kind of scenario would happen where the KAV is smaller than the porosity. So starting with case 1, this is when the centers of solute molecules are unable to reach the solid surface in void volume space. So the difference in total volume and available volume can be estimated as the product of the area of the solid surface and the distance between the solute and the solid surface. So this kind of image over here to the left, the circle is the solute molecule, and then this would be that distance between the solute and the solid surface. And the distance delta is equivalent to the radius of the solute when this solute molecule is able to actually reach the surface. However, there are some cases where the solute molecule and the solid surface have the same electrical charge. And in that case, the molecule won't be able to actually reach the solid surface, and delta is actually going to be larger than the radius of this molecule. Case 2 is when some areas of the available volume are smaller than the size of the solute molecules, so then the solid molecules are just not able to actually reach through those pores. And then finally, the large penetrable pores for case 3 are made inaccessible because they're surrounded by pores that are smaller than solute molecules. Next, I'm going to be talking about the partition coefficient. So this is the ratio of the available volume to the void volume. This partition coefficient measures the distribution of the solute at equilibrium between the void space and the external solution. So this is different than the partition coefficient that's used in chemistry, which is used to describe the partitioning of solutes between 2 liquid phases. The partition coefficient for porous media is related to the ratio of the available volume and the porosity. So that's denoted here. Finally, I'm going to do an example. So for this example, we want to determine the partition coefficient and the available volume fraction of a spherical solute in the same porous medium as example 1. Assume that the diameter of the solute is B and the electric charges and interactions are negligible. So first we have our void volume in each cylinder, which is this L pi d squared over 4. And then we have the available volume denoted here. So we know that for the partition coefficient, it is just the available volume over the void volume, which gives us this final answer. And then for our available volume fraction, we do the available volume over the total volume. So we have the available volume over the total volume, and that gives us that answer here to finish the example.
Hi, I'm Sarah, and I'm going to talk about Darcy's Law. Darcy's Law was discovered in 1856 when Darcy set up a vertical column filled with sand with water inlet at one end and an outlet at the other end, and applied the pressure difference at the inlet and outlet ends of the column using constant water levels H1 and H2. By measuring the flow rate of water through the sand under various pressures, Darcy observed some consistent relationships. He observed that the flux of water Q was directly proportional to the difference in water levels from inlet to outlet. And he also discovered that the water flux was directly proportional to the cross-sectional area of the tube, and that the water flux was inversely proportional to the length of the column. And by combining these proportionalities, it led to Darcy's law, the law that describes groundwater flow, where Q over A equals K delta H over delta L, where K is the hydraulic conductivity and Q over A is Darcy's flux or Darcy velocity. So based on a series of experiments, Darcy discovered that the flow rate through a saturated sand column was proportional to the pressure difference in the system. But Darcy's law has its limitations. It's invalid for non-Newtonian fluids, Newtonian fluids at high velocity, and gases at very low and very high velocities. That is, Darcy's law is only valid for laminar flow when the Reynolds number is less than 1, and not valid for turbulent flow. There are two approaches to describe fluid flow in porous medium. One is the numerical approach, and the other one, proposed by Darcy, is the continuum approach, where we imagine that the porous medium as a smooth and continuous material with three length scales. L is the linear dimension of the porous medium, and small l is the linear dimension of a small volume in the porous medium, and the size of the pores, which is the average distance between adjacent pores. And big L has to be 10 times bigger than small l, which has to be 10 times bigger than the size of the pores. And to know these length scales, we choose an elementary representative volume, ReV, from the porous medium, which can be taken to be a point in the material. And here it is represented by the dotted line. Now, to solve fluid flow problems using Darcy's law, we need to understand the governing equations. First, the fluid flow must satisfy the mass conservation law, and the mass balance is represented by this equation, where the divergence of fluid velocity vector equals 0 when the fluid production minus the fluid consumption equals 0. And the momentum equation is Darcy's law, where the velocity equals negative h, the hydraulic conductivity, times the gradient of the hydrostatic pressure. And by combining the mass conservation equation and the momentum equation, we get this equation generalized for a fluid with production and consumption. And when there is no production or consumption, the equation reduces to this. Now let's apply Darcy's law to an example. Here we have saturated sand and an inlet and an outlet of water Q, and we need to find the velocity profile. We know that this is a one-dimensional flow through a porous medium, which is the sand, and the sand has a hydraulic conductivity H. Now to solve this, we know that the velocity equals negative h dp over dx, and we assume that the rate of production and consumption equals 0. And from this we get that the second derivative of pressure equals 0, and we integrate this twice to get the pressure profile with unknown constants C1 and C2, and we use the boundary conditions to find C1 and C2. The boundary condition 1 is P at x equals 0 is P naught, and P at x equals L is PL. And we plug them in to get C2 equals P naught and C1 equals PL minus P naught over L. And using Darcy's law, we get that the velocity equals negative h PL minus P naught over L.
Hi, my name is Schorge, and I'll be talking about the Brinkman equation. And this is just a bridge between the Darcy and Stokes equation, which is just adding the viscous dissipation term to Darcy's law. And this is used if the permeability is unknown or if it isn't too large or small enough to simplify this entire equation. So case one is if there's a small permeability, and if this is the case, then the viscous dissipation can be neglected, and this will just simplify Brinkman's equation to Darcy's law. Another case is if there's a large permeability, and in this case, the viscous resistance at the fluid-solid interface can be ignored. So in case two, the entire system would be treated as a fluid flow without any porous media at all, and it would just be reduced to Stokes' equation. An example using the Brinkman equation is here. Assuming there's an interstitial space between two cells, which is considered to be two parallel plates, the hydraulic conductivity is defined as a ratio of fluid flux to the pressure gradient, and it depends on K and interactions with the wall. And the channel height H is much smaller than the cells, so the flow is unidirectional, and you are to derive the velocity profile and H as a function of K, H, and mu. And the solution is to start, you use the continuity equation to show that Vx equals Vx of y, so Vx is a function of y, and you can use the Brinkman equation, which is the governing equation, to show that in the x direction, mu times delta squared Vx over delta y squared minus mu over k Vx minus dp dx equals 0. And since Vx is independent of x and p is independent of y, the right-hand side and left-hand side of equation 4 must be equal. And for this to be the case, both sides must be independent of x and y, which leaves us with a differential equation that we will solve using a homogeneous solution and a particular solution. On the left, you can see there is a diagram of this situation with the two cells acting as two walls and a fluid flow in between them, and there is a distance h. And to find the homogeneous solution, you use the characteristic equation to get your homogeneous solution. And then for the particular solution, you have to use guess and check to get negative k over mu times b. So the overall velocity profile is C1 sine h y over root k plus C2 cosine h y over root k minus k over mu b. And this gives us equation 6. And to find C1 and C2, which are constants, you have to use the boundary conditions, which one is by symmetry. So the change of velocity over y is 0 at h over 2, or at y equals 0. And for the no-slip condition, we use Vx equals 0 at y equals h over 2. And you just plug in these boundary conditions, and you can solve for C1 and C2 to give us equation 7, which represents the overall velocity profile in terms of y. And to find h, we know that h is q over the pressure gradient b. So to find q, we just take the integral of Vx over y and divide it by h. And once we have this fluid flux, we can divide this by b to get our final value for h.